Okay, hello, welcome to the session. Today we will talk about 3D printing, teaching Java and also Groovy, and visual programming and how you can put that together. First we'll talk about 3D printing, the technology that's used in such a printer you can see here, and then we are going to discuss designing and actually coding 3D dimensional objects for the printer, because this is one of the most complex part actually. And then I'm going to introduce you to visual programming with VRL Studio. This is a text-based and visual programming IDE that I developed at university. Then I'm going to show you a small project that uses 3D printing. It's the Pi on Wheels robot, and it has a nice JavaFX user interface, and you can print the parts and customize them. So it's also ideal for teaching Java in the context of IoT. So a few words about me. I'm doing my PhD at the Goethe Center for Scientific Computing at the University of Frankfurt. And my research interests are developing visual programming concepts. So I use Java and a lot of its advanced technologies like reflection and compiler infrastructure, and also the Groovy compiler to create visual programming environments. And the projects I'm working on is VRL Studio and vWorkflows, which is a workflow and graph library for JavaFX. And also I contribute some components to the JFX project. Yeah, you find me on Twitter. My handle is mihosoft, not Microsoft, it's mihosoft. And the webpage is also mihosoft.eu. Okay, now 3D printing. Have you all seen a 3D printer in person, or was it your first time? So what's the experience? So only one person saw a 3D printer? No, more. Okay, a few at least. So this is my 3D printer that I have in my office. It was a do-it-yourself kit, and it took me just 1 or 2 days to assemble it. And what you can see here, the orange stuff here is actually the parts that you're going to print. And here you see the nozzle attached to the extruder head. And here you see 3 nozzles, just as an example. They have a small hole in the middle, and they're melting plastic wire, just like the wire you can see here. So I'll take that out. It's just PLA wire that you heat up to 210 degrees, or a bit more or less, depending on what you're going to print. And let me put that back. Yeah, and then this goes through this. It's just a plastic part. It goes through here, and then it's heated here, and then it creates the objects layer by layer. So here you see a 3D part, and you can see the actual layers here. So in this case, they have small holes, but if you do it right, actually you don't see the holes here. But what's interesting about this part is that I was able to put it under an electron microscope. So these are very expensive, but a friend of mine has it, Alexander Heusel, so thanks to him, I could create these nice images. And you see here, we're just here at this point, and we're magnifying it, so you see here like half of the image is like 2 millimeters, and then we're zooming in and out. And you can see the layers here as well. So this technology is called FDM. So we are adding material on top one of another. So usually, if you do machining, you did like reducing, subtracting stuff from a metal block or something, and this is what's used in industry. But for prototyping, it's actually much better to use something like additive adding plastic, one layer on top of another. So this additive manufacturing, that was the word, gives you the opportunity to really build structures that were not able to build with any other technology, like these here, for example. They have some parts that overlap, and you couldn't just do it by removing stuff because you're not able to drill inside of these small holes. I don't know if you can see that, but I recommend you come later and have a closer look. And also something like this gear mechanism. It comes out of the printer like that, so you have to break it to actually take apart the gears. So it's also fascinating and kind of a novel technology. The only problem is, how do you create 3D geometries? So who of you do 3D modeling yet? Okay, so quite a few. But still, I mean, if you do something like these patterns here, it's rather complicated, and also because you have to adjust spacing and stuff. And then you have to generate the patterns with different parameters depending on the plastic you use. And therefore, I mean, you can use professional CAD applications, of course. You can do that, like use the industry standard applications. If you do it as a hobby or for teaching, you can also use Blender for modeling, but this is more like for designing stuff and not really producing patterns. And then there's a program called OpenSketch, which I used for quite a while. But I actually like to program in Java and JavaFX. And therefore, I created a library called JCSG. And the J, of course, stands for Java, and JFX for JavaFX. It's all open source. So the basic concept is very easy. It uses Boolean Operations as the basic set. You can do a union operation, like here. So we're doing the union operation on these two circles. You can do a difference, like subtracting a circle from another circle, and intersecting those. And you can create the hull operation. So you have two different parts, and you're kind of wrapping them. This is how the code looks like. So in this case, we just create a cube. All objects are basically called CSG objects, and they contain the polygons and everything. And you create a new cube and say to CSG, then it's rendered as multiple polygons. That's what we have here, so just a cube. And now if we change that, we have a sphere, like that, and now we can do some nice stuff like combining both, and that looks like this. And we can also transform it. So in this case, we have the sphere like before, but we are transforming it by 1, so it slightly changes the position. So here is the difference operation. So we are cutting out a sphere out of the cube. Same objects like before, but here we changed union to difference. Another example, so we shift it again. We use the translate X again, and then we get an object like that. And all that is done in JavaFX, and I use Groovy for compiling that code on the fly. And here you see the intersection. And then we can do the same again. So we're translating the sphere by 1 again. So in here you see the hull operation. So the sphere has been slightly modified, so we're using a different radius. So it's a mix between sphere and cube, and of course we can change that to something like before. So it looks more like the cube, and if we use a bigger sphere, then it gets more sphere and less cube. So you can kind of morph between objects as well. And there we also have the different examples, like we shift it here by one again, and then we wrap both objects. And here we just use two spheres to make this little nice capsule. And yeah, that's basically JCSG. Now I'm going to introduce you to Visual Studio, just give a brief introduction because it's a general purpose visual programming language and environment, and then we're going to look how to combine the JCSG software in Visual Studio to actually create stuff. So VRL is a framework for automatic GUID generation. If you give it code or compiled objects, it will always give you a user interface for that. I'm going to show that in a minute. And it allows you to do visual programming and workflow management. Yeah, and the automatic GUID generation works like that you have an object inspector that's capable of creating 3 different types of components, like it can create windows and like subcomponents for methods, and then the individual visualizations for input and output parameters. And this object inspector communicates with the Java objects and the binary objects on one hand, and then with the UI. And if the UI changes, it transfers that back to the actual objects and invokes methods and stuff like that. Okay, now demo. Let's just see. Here we go. So what you see here is what we call the canvas. And yeah, now let's just create some sample code. In this case, just a hello world method. So like this. So we are only concentrating on the method. It's just a class with some serializable stuff in it. And if I compile that, we get a user interface like that. And you can instantly interact with that. You can just invoke the method. You don't have to think about make files or Gradle scripts or JVM and anything. So, and that's why I think it's really useful for teaching. So now let's do something else, like we can add numbers, for example. So these are just basic examples, but you can visualize any Java object. It can come from any library, or you can compile it yourself on the fly. So let's create an instance here. So let's type in a few numbers, and now we can actually create another instance, and we can define a data connection between those. So it's a dependency. The second one depends on the first one. So let's add one again. So that's basically it. And also what's really nice about it is that you can always access the source code again. So whenever you have a component that's built inside the environment while it's running, you have the source code at hand. So you can just click on this Z icon and you get the source code. And of course I can change it. So let's change it to times, A times B. And then yeah, you get different results. And let's try different values as well. So you can really like change it on the fly and experiment with it and do prototyping for your software. And all the projects can actually be exported as a jar file as well, and you can write plugins for it. Then what you also can do is you can very easily create 3D objects in it. So in this case, we are just going to create a few nodes, and we are defining triangles, and we're returning the result as geometry. And also here, the VRL framework knows the data type and gives us a nice 3D visualization that we can interact instantly with. And of course, you can also write something like function plotters and stuff with it. And that's also what we do at university for teaching algorithms. Yeah, what else to show? You have a component manager. You can search the components. Like if I search for add, then I get this add integer component. And also if the description or the package name contains the word add, so like here it's the description, then it shows the components. And so the user doesn't have to think about where to put the source file. You just open a window, type in the code, compile it, and run it instantly. And then it lets you combine all that stuff. What it also does here is it creates versions for you. So you don't have to think about checking that into a source code management system like Git or SVN or whatever. You just let it do its work, and you can give it custom messages if you like. And there is a Git repository in the file format, so it's packed into the jar file. And if you send it to somebody else, then you send the whole history, if you like. So here, let's just see, it's just an ordinary file, and everything you write is just inside a jar file. So the compiled classes, the source code, some XML for the UI states, and so on. Okay. So now let's have a look at the JCSG plugin. So here you see something called cube creator. We have that cube, and we can define its dimensions. And if we look at the actual source code for that, let me just look that up. It's here in that project. And I think here, cube creator. It's a very small class that just returns the cube, as you've seen before. It creates a new cube and then calls to CSG, like in the slide version with JavaFX. So it's very little work to actually integrate that if you have a basic integration for the parameter types. So if you want to write your own plugin for different file format or other data types, then you basically just write the visualization for the parameter, and then you're done, because the system will compose the user interface for you. And so this was the cube creator. Then we can use a sphere creator. We can also give it a radius, and we can change the resolution. So let's use a lower resolution. You get a sphere like that. And then we have a cylinder creator, and also some for other objects. And the cool thing also is that you can also write your own algorithms that create more complex geometries, and then you can combine them, as we've seen before. So now let's try to check out the different operations again, like union and difference. Here we have a cylinder and a sphere, and we are transforming the sphere, so we are translating on the z-axis, and then we get something like this here when we do the union operation. And this is a ring, actually, but with curvature inside, because we subtracted the sphere. Here you see the intersection of it. And here is the hull of the thing. So make it a little bigger. Looks like that. So some of these objects are actually not that easy to print. So what do you think? Which objects will be printable out of the box? Like first, second, third, fourth? Yeah, so this one here prints nicely, and this one here, right? And here you might have a problem, like printing it so. You might be able to print it like that, so you can put it in on the printer like that, and then hope that the angle is not too problematic. In many cases it works, but it depends on how the heat bed works, and also the resolution of the object, because here, if they are too small here, you won't be able to print that without support, because it will just roll out of the printer. So you really have to think about how you design the objects when you try to actually do that on the printer. And then in the end, we're just going to select one object, and we are going to save it as STL file. And what you can do then is you can give it the printer software. So here it's a different geometry. So we're going back once, and let's try to make that bracelet that you just saw. So here we are using the cylinder creator again, creating this flat cylinder. And then we use another cylinder, and as you have seen here, or as you also can see here, we are subtracting small cylinders from the bigger one, okay? And what we need to do now is to have like copies of this smaller cylinder to form a circle. And therefore, you can actually write your own extensions very easily, like here. It's only a few lines of code, and as I mentioned before, you always get the user interface for the code you write. Of course, it has to compile, but that's the only thing you have to manage, and everything else will be done for you. And what I didn't show, and what I should probably show, so that you're able to understand these annotations in the code file, let me show you some other example, like a color chooser. So if you write a color chooser, or request your students or children to write a color chooser in Swing or JavaFX or whatever, it's really too complicated probably. But here, it's rather easy, because you just have to know how to create an instance of a color. You give it the RGB channels, and then, you can annotate it to request something like a slider, but you don't have to. It will work anyway. So if I compile that and create an instance, you get this nice color chooser, and it returns a color. So that's really easy. I mean, just a few lines of code. If you leave out the annotations and stuff, then it's maybe 5 lines of code for a whole usable component. And in this case, it's a bit more, but still not very much. Basically what we do is we're giving it a radius for this circle that we're trying to create, then an angle. In our case, we're using just a full circle. And then you give the number of copies of the object. And of course, here the first parameter is the actual CSG object itself. And then here inside that loop, we transform the CSG object by the radius, and then we are rotating it and using this step size we defined here. And then we just create the union of all objects. So if the objects that we defined above here is null, then the objects is just the first objects, and otherwise the objects are just objects union and then the new object. And then this will return a CSG that consists of this circle. And then, so let's remove the color chooser and see what we can do next. And here we can just use the difference operation. And that's basically it. I mean, we used difference, and then the only thing we need is the STL saver, and then we are done. We have our bracelet. And we can then open that in the printing application. And usually it looks like that, just we expect it. But then we can tell the program to just leave out bottom and top layers, and also we can tell it to just don't fill it. So we only see the path, and if we visualize the layers, then it's like this. So now let's start the printer, and when we are done, it should be, we should have a bracelet. So it needs to heat up. It will take some time, but I think it will work. Just takes about a few minutes, and then it will start moving the print bed, and then start putting one layer on top. So, and of course you can do anything with it. You couldn't not only use the difference, you can of course look for union, for example. Use that one. Again, we use this cylinder and then the circle. And like with adding numbers, it's just the same basic concept. And we get something like this. And of course, we could also use the hull operation and the intersection, actually. So, do you have any questions about the visual programming environment? Is there anything you... Yeah?
The cube you just showed, is that a solid cube or just layers of 0 pixels?
So actually it's just polygons. So it's not filled, but the printing software will fill it. So it just has to be a closed surface, and it will assume a solid object, actually. And if you don't want one, like we did with the bracelet, it's assumed to be solid, but then we can tell the software to just print the outer boundary. And you can also say, like, fill it with 30% or 40%, depending on how stable the object should be. Yeah, that's basically how it works. So let me just point you to the web page. This is the VRL Studio web page. You find there all the information. You can download it. It's a completely open source, and you can also contribute if you like. I created some videos that shows the most important features. And so we have visual reflection. We have this workflow engine. We have an integrated editor that also has some auto-completion functionality. And then, of course, you can always drop objects on the canvas to visualize objects, which is also some kind of introspection, like you have in the editor. Then we have a plugin infrastructure, so basically any Java library can be turned into a VRL plugin. We have versioning support. You can export libraries. And we also have a shell and a debugger inside, so you can actually really do bigger projects as well. So now the printer starts. It's supposed to poop in that corner here. Yeah, it does it. Yeah. Okay, we just let it do its work. Yeah, what I'm going to say was here we have some examples like a function to deplotter, even a sound generator. You can feed mathematical functions to your sound card and explore them. This is really nice for teaching math and physics. We have a 3D function plotter example and also some OpenCL programming with Groovy and yeah, the OpenCL binding to Java binding. Yeah, that's VRL Studio. We have also some documentation online. So you see the most useful shortcuts and how you control the workflow and so on. So, and we use it for teaching students mainly, but you could also use it for teaching children or for prototyping. So what I like to do is just explore ideas, and sometimes you just keep it that way, or sometimes I also port that applications to regular desktop applications. Yeah. Any other questions about that? Oh. There is one. Okay, I just can't see it. I don't hear you, actually.
Okay, I'll try a little bit louder.
Yeah.
When you mentioned children, what age ranges are you
Like maybe more teenager age, because they are supposed to write source code actually. But if you prepare something like we did here in this example, you could even go, I think, like 10 to 12 years old and teach them stuff. Then they would probably only use the visual programming and just change a parameter or so, and then still they could have their own bracelet and be happy with it. So yeah. Okay, then let's go back to the slides. Oh. Let's see. So we did that. So now I'd like to talk a little on the Pi on Wheels project. I also showed that at Java 1. I thought about a rather small and affordable robot platform that involves 3D printing and a little programming as well. And this is how the robot looks like. Maybe some of you have seen me printing wheels or Raspberry Pi mounts or stuff like that. And these are the parts that you need. So of course you need a Raspberry Pi. You need 2 servos, and I'll also explain that how you have to modify them, that they really work as a motor. Yeah, the other electronics are 2 resistors, then an LED for showing the status, an infrared LED for communicating. This is not really necessary, but we made some extensions to it, so you might want to buy that as well. Then some battery for charging mobile phones or something. Then a small breadboard and a few cables. And then, of course, you need all these red parts that are printed. So when I designed that, I started with the Raspberry Pi mount. I have one here. Looks like that. And I have one for Model B and B+. So you just have to print them. You don't have to modify them. We verified they will work on most printers. And then you have some breadboard holder and battery holders that you can just attach to the Raspberry Pi holder. Yeah, and that's basically it. You just add the servos that you can see here. So it has its own servo mount, and yeah, then we use a breakout cable for the Raspberry Pi. But how do you turn a servo into a motor? So here are some instructions. It's not that complicated. You can always buy servos that have full rotation support, but they are more expensive, and I just take them apart and build my own motors. So you just open the servo, then you see the gears here, and here's some resistor that we have to pull out. So the problem here is that with this gear, it blocks from rotation to make sure the resistor won't break. And you just take that apart, just use a knife or something, and then you have to actually push in this resistor, so just push it out of the way and make sure it's in the middle position, roughly, so the servo will stop if you go to the middle position, and then you can control it to move backwards and forwards. So yeah, and this is the servo mount that you use these here to attach to the main frame, and then yeah, you put in the servo. Yeah, the servo uses a pulse width modulation, and you can create that on the Raspberry Pi. I tried software pulse width modulation because the original Raspberry Pi only has one pulse width modulation GPIO pin. But then I experienced that it's not precise enough and also uses a lot of CPU. So I integrated a project called Pi Blaster and Servo Blaster, which is just small libraries, and they are part now of the Java API here, so you don't have to worry about compiling C code or stuff. It's already done. And then, yeah, you can create this pulse width and frequency. So the frequency is about 20 milliseconds, and the pulse width is 1 to 2.5 milliseconds usually. And then you can control the movement of the servo. And this is the full circuit, actually. So it's not very complicated. You just have to power the servos and attach the signal wire to one of the GPIO pins. And you do that with the second servo as well, and then with the status LED. And yeah, that's basically it. So now the software stack. The Pi on Wheels comes with a server application that you just run on the Raspberry Pi. And then we have an API that allows you to remotely control the Pi on Wheels robot. And I also created a small IDE with help by Garrett Grunwald, who created some of the really nice looking controls that I will show you later. And I also integrated JCSG into that IDE, so you don't have to use JCSG separately. You can just use this program also for teaching and tell children or students to change the wheel size or something else to customize their robots. Yeah, I just started with the Raspberry and Noob image, and yeah, you just can download the server and lab applications. To run the server, you just download it and yeah, basically run the POW server script. And if you want to make that permanent, you can just add that to etc. RC local or something like that. And then you reboot the Pi and will start that service automatically. So here are some screenshots. This is the connection tab. So the application will just scan for Pi on Wheels devices on the current network. So if you have more than one, it's also no problem. They are controlled simultaneously, so it's kind of broadcasting. Interacting with it, so here you see the nice control done by Garrett. It's a radar control, and here, yeah, you see this small API. You can move the robot, you can turn it left or right, And you can also control the status LED to give it some feedback. And yeah, you can save these small scripts. They are also Groovy scripts. And of course, you can also do that from Java and yeah, write your own applications if you like. So, and here is the JCSG integration. It uses JavaFX for visualization. This is something that I didn't mention, that the JCSG is instantly capable of converting the geometries that you define in your code to JavaFX nodes. So you don't have to think about using JavaFX 3D yourself. You just get a node that you can add to a container, and yeah, that's it basically. And then you can export these designs as STL files that go to the printing software, and you can also export as PNG for adding it to slides like I did here. Yeah, so no, we're not completely done yet. We're waiting for the bracelet to finish. So it's probably done in 3 minutes. Yeah, are there any questions about the robot actually, about the project? No questions? Yes, there's one. I didn't see you. Yeah, you can drive in the room, and we also have an extension with XP devices. So they have this an infrared sensor, so you can do some triangulation and then estimate the position, and you can interact even with multiple robots, like they could see each other, and yeah, things like that. So, but we try to keep it a low-cost project so that really schools could afford multiple devices, because in many situations it's the problem that yeah, schools have problems affording a printer and the hardware and stuff, and this makes it really easy to just not only buy 1 or 2 of them, but you can probably buy like 5 or even 10 of them, so that children can actually play with it and not just see the instructor playing with it and then they have to stand in one line and probably just get access to it for a minute or so. So that's why we keep it really simple. But of course, you're welcome to contribute stuff and make it more complex, adding extensions to it like Arduino breakout stuff and doing more IoT stuff with it. And also the code is all open source. So the slides you saw were also done completely in JavaFX, and you saw the interactive 3D integration. And yeah, most of it is just BSD, so you can basically do whatever you like with it. The Pi on Wheels project is also on GitHub, and yeah, just download it and use it for your stuff. And yeah, then I'm actually done with the main talk, and I welcome you to watch the printer and come here to see some of the incredible pieces. So it just finished actually. And yeah, I have a few pieces to give away. So those, I will keep those, but I will give away all the other pieces. So if you come here and like to take some of the plastics or see the new bracelet we printed, then yeah. Okay, thanks.